Okay, so we are in computational geometry, and I want to talk about the visibility graph. It's part of usually motion planning, for example, for robotics. So let's talk about the algorithm of visibility graph. Now, just before talking about exactly how the algorithm works, let's see what is the visibility graph. So if I have some polygons, think about, for example, a robot that tries to get to a destination, and there are obstacles that are polygons in the landscape. So let's assume that it starts here. This is our robot, and the end is right over here. This is the destination. So the visibility graph will let me see what the vertices and the edges that can connect the points, the vertices on the graph. The idea usually is that I want to find the shortest path in this space, and using the visibility graph I can find this path. So the visibility graph connects those vertices that are the vertices of the polygons. The polygons are usually the obstacles. Here are the vertices. I draw them in red circles, and the start and end position are also part of the, let's say, vertices. Let's denote them as V, the set of vertices. And now I have also edges that connect those vertices that can be seen without crossing any obstacle. For example, this vertex and this vertex, they cannot be connected because they cross an obstacle. So this connection won't be in the visibility graph. But for example, this one and that one, 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 this one and that one. You can understand there are very many options, and I can connect many vertices that can be connected without crossing any obstacle. Again, this one and I don't know, for example that one, they are cannot be connected because again I'm going throughout an obstacle. So it can be this one, and that one also cannot be because I need to cross the obstacle. Note that this one and that one are connected, 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 this one and that one are connected. So the vertices that are neighbors in the same polygon are connected. This one and that one is connected, this one and that one is connected, this one and that one is connected. So every two vertices that can see each other and make an arc or an edge between them without crossing any obstacle are connected and part of the visibility graph. We can make many more connections, but let's stop here. So we want to find and build this graph. Now after I build this graph, I can use it to plan and find the shortest path. In each edge here I can put what is the Euclidean distance for each edge. For example, this one, I don't know, 2 meters, and this one, I don't know, 5 meters, and this one, I don't know, 3 meters, and this one is 1 meter, and this one is 1 meter, I don't know, 2 meters maybe. And now I can find, for example, using the Dijkstra algorithm for finding the shortest path in a weighted graph with non-negative weights. So I can find, for example, this path that may be the shortest path from the origin to the goal, or maybe this is the shortest path, maybe this one is shorter. Yes, so the Dijkstra will try will look at the different path and find the shortest path on this weighted positive weights visibility graph. So this is why we need this to plan and to find the shortest path. Note that the obstacles are closed sets. I can touch, the robot can touch the edges of the obstacles. So let's turn to making the visibility graph algorithm, which gets the vertices and try to build the edges between them when looking on each two vertices and seeing if the edge between them cross or doesn't cross an obstacle, and if it doesn't cross an obstacle, so it can be part of the visibility graph. So let's see the algorithm now. Okay, the algorithm again is the visibility graph. What we are getting is a set. This is the set of vertices. Let's call it S. Okay, now this is the input. As we said, this is the S, and this S is the, let's consider it the polygons, not the vertices, disjoint polygons. Now the output of that algorithm will be the visibility graph that we will make it like this. Okay, the visibility graph of the polygons S. Okay, now the start and the end points, let's not count for them now. You can add them, there is no problem. Let's start the algorithm. In the first step, what we're going to do is initialize the graph. Initialize G as V and E, where V is vertices of our polygons and E will be the edges, and we'll start it with an empty set. Okay, this is V and this is E, and this is the visibility graph that we build from V and E. Now the second step is to go throughout the vertices in V. So for all V in V, do, it's a for loop, so maybe so it will be very understandable. Let's write the word for, so we know that we are in a for loop. So for all vertices V in V, what we're going to do, the next step is W will get the visible vertices, which will be a function that gets the vertex that we are on now, v small v, and the set S of all polygons, and will tell me what are the vertices that are visible from the current vertex that I'm on now, namely which vertices I can see and draw an edge between them without crossing any obstacle. Those v1, v2, those are visible one to another. So I look for the current v that I am, all the vertices that are visible, namely I can draw an edge without crossing an obstacle between the two vertices. So this is a function that I'm not going to explicitly write it down now. This is called visible vertices from a vertex V with polygon S, but this is the idea as I draw now. The next thing that I will take every vertex in this set W that has all the vertices that can be seen from the current vertex V, and create an edge between the V and each vertex in the W set of vertices that can be seen from V. So we are doing it for every, let's say, vertex W in W here, this one. We will add an arc. That will be called V2W, and I will add this arc to the set of vertices in the visibility graph. I will add it to E. Remember, E is here. This is part of the visibility graph that I'm building. Okay, and after I go throughout all vertices and build all the edges and insert it to V, I am done in building the visibility graph, and I will return it because we are finished. Return the visibility graph G, and that's it. This is the visibility graph algorithm. Just building it, finding the vertices for each vertex of the polygon vertices, find the vertices that are visible from each vertex and connect them, and the arc between these two vertices that can be seen to the E, to the set of vertices in the visibility graph G, and return the G. Do it for each vertex in the map and you will get the visibility graph, which is built from V, the set of vertices from the polygons S, and the set of edges between the visible vertices V. That's it. This is the algorithm for the visibility graph. I didn't show again the visible vertices. How do I find for a single vertex all the vertices that are visible, namely line between them won't cross a polygon, won't cross an obstacle, but that's okay. This is not for now. This is another algorithm. This was the visibility graph algorithm. Thank you very much. If there are any mistakes or corrections, please tell me. And this is it. This is taken from the book. This algorithm taken from the book Computational Geometry, Algorithms and Applications, 3rd edition. Thank you very much, and that's it.